pick-up y delivery en tus compras, toma de presión y glicemia gratis en todas las sucursales, además de la mayor red de farmacéuticos para garantizar tu seguridad. Farmacia Carol. Con Carol cerca, te sentirás más tranquilo.
Nosotros somos Padana, una empresa de panilería italiana líder en el mercado. Ofrecemos lo que son las soluciones para las salas limpias. Todos nuestros productos son confeccionados en Italia, tenemos todas las certificaciones y se hace todo a la medida.
Somos una empresa dedicada a suplir laboratorios de química, física y biología, toda la parte de los equipos analíticos, cristalerías, plásticos, reactivos químicos, materia prima, la instrumentación en general en equipos de laboratorios, todo lo referente al laboratorio de química, física y biología.
Hola, ¿cómo están? Mi nombre es Richard Garavito, subgerente comercial de la empresa FETTE. Hoy les vengo a contar un poco de qué es lo que hacemos como compañía. FETTE, su casa matriz se encuentra en Chile y sus representantes internacionales en toda América Latina. ¿Qué hacemos nosotros? Nosotros formamos parte de un holding que se ha enfocado en los últimos 30 años al desarrollo de servicios y productos de fácil aplicación para industrias altamente reguladas. ¿Cómo lo logramos? Eso lo logramos de la mano de una red de especialistas, acreditados y ubicados en diferentes partes del mundo, todos con experiencia comprobada para apoyar de manera eficaz y efectiva los desafíos de infraestructura y calidad de nuestros clientes. En técnica entregamos arquitectura y ingeniería de valor, brindando soluciones para proyectos de ampliación, dimensionamiento, asesoría y ejecución de obras para plantas industriales. Vamos dejando de esta manera nuestra huella en la industria farmacéutica latinoamericana con más de 200 proyectos desarrollados que equivalen a alrededor de 750,000 metros cuadrados en planta productiva. Gracias por escucharnos y esperamos que entiendan sus desafíos y que puedan trabajar con expertos.
Business comes in all sizes. Customers may be just around the corner from your company or halfway around the globe in faraway markets. From single standard shipments to large volume transports, complex logistics and supply chain solutions, DSV is but a click or a call away. In more than 80 countries around the world, on land, by air or by sea, we protect your shipment and support your need for speed. Even heavy cargo is easy to handle with our online services, and our experts are used to addressing the elephant in the room. So if you think big, you should think DSV. We offer a competent partnership that gets things moving. For small startup businesses, for large corporations, for anyone with towering ambitions. you need it, we move it.
It's existed for almost 70 years. A passion for development and realization of new ideas and solutions. That is why FETTE Compacting is the world's leading provider of integrated solutions for industrial tablet production. Since 2016, the product portfolio has been extended with highly efficient capsule filling machines. More than 5,000 installed machines proves every day that the highest productivity and the best quality match our clients' demands. More than 100 highly specialized service technicians and application engineers provide customers worldwide with access to our entire wealth of expertise. That has turned us from being just a machine manufacturer into a global market leader. Trend-setting, service-oriented, highly skilled.
FETTE Compacting. Be efficient.
Aquí tenemos una breve representación de lo que somos, presentando las líneas texto para lo que es monitoreo de flujo. Tenemos también Beckman Coulter con el TOC en línea y el contador de partículas en el aire.
Maxicina es una compañía italiana desde 1974 dedicada a la fabricación de equipamiento para el acondicionamiento de producto primario, ya sea para líquidos, asépticos o no, sólidos, semisólidos y además en máquinas para empaque secundario.
PQE somos una empresa de consultoría integral 360, ofreciendo una serie de soluciones para la industria farmacéutica a nivel de cumplimiento, siguiendo estándares internacionales. Nuestro principal negocio es la validación de sistemas computarizados y el tema de integridad de datos.
Nuestra empresa Saniagua trajo a esta exposición la soldadura orbital y la inspección endoscópica, con el objetivo de garantizar los montajes de la industria farmacéutica.
Bienvenidos a Farmaweek 2020, una expoferia enfocada en la capacitación de la industria sanitaria. 3 días, 15 conferencias a través de la plataforma Zoom. Acompáñanos, disfruta la experiencia. Welcome to Farmaweek 2020. This is an expo fair focused on the training of the sanitary industry. This is going to be for 3 days. We will have 15 conferences, so you don't want to miss this. It's going to be through the Zoom platform, so we hope to have you there so you can enjoy the experience.
Segunda edición de Farmaweek en este 2020. Vamos a continuar con la segunda conferencia del día de hoy. En esta ocasión tendremos la participación desde Alemania de Ana farmacéuticas por la Universidad de Hamburgo en Alemania. Es científica en PhD. Es miembro del grupo de manufactura de aplicaciones FETTE Compacting. Además es líder mundial de y procedimientos orales. En el día de hoy, Ana estará tratando el tema herramientas de PAT, Process Analytical Technology, el camino a adquisición de datos en tiempo real. En esta conferencia se va a estar utilizando el servicio de por si quieren escuchar el audio original. Recordarles que también esta conferencia llega a ustedes gracias a la gente de FETTE Compacting y vamos a iniciar con la participación de Ana en este momento. Welcome to once again, Ana.
Thank you, Marilyn, for the kind introduction, and hello, everybody, and welcome to my talk about PT tools, a road to real-time release in a tablet production. And I would like to show you first how my talk will be structured today. in theory. So I would start with an introduction with a background, so you get a short overview about PET. Then I would like to introduce you our direct compression line, because most of the studies that I will show you today were performed on that line. Then I would like to talk with you about process analytical technology research projects, and that we currently are performing at FETTE. And then I would like to show you some case studies that we have performed on our own or together with a customer. But before I start with PET, I would like to give you an overview who is actually FETTE. And FETTE is a tablet press manufacturer, and we are in a tablet business for quite long. But maybe I would like to show you a timeline of evolution of the tableting technology. So, for example, in 1948, there was a one-stroke tablet press. In the 60s, double-sided rotary tablet press followed. In the 80s, FETTE introduced the first worldwide computer-operated tablet press. In the 90s, FETTE released our I-series. It's the most known tablet presses of us. It's, I would say, our
Anna?
working horse. Yes?
I'm sorry to interrupt. I just wanted to verify if you are sharing your screen, because we are not able to see it.
Actually, yes. Let me double check that, maybe.
Please, thank you.
Let's start from the beginning.
Okay.
So, can you see my screen now?
Perfect. Now we can see it. Thank you very much.
So I hope it will stay like that. If not, please let me know. Good. Once again, welcome to my talk, and I would continue with the structure. And my talk today is structured that we will start with introduction, then direct compression line and PET technology and the applications of the PET. And what I actually showed you, and I hope that you have seen that, I'm sorry if not, is our timeline of the evolution of the tableting technology. And there you see once again the single stroke tablet press that was released. And then you see that the tablet press from the 60s, that is a double-sided rotary tablet press. Then the first worldwide computer-operated tablet press, which was introduced by FETTE. Our working horse from the 90s, it's our I-series, and our premium tablet presses, it's our E-series that we released in 2010s. And now I would suggest, let's go to PET. But before we start with the process analytical technology, I would like to give you a definition of what is process analytical technology. And process analytical technology is considered by the agency as a system for designing, analyzing, and controlling manufacturing through timely measurements during the production. And it is also the goal of the PET is enhancing and understanding and control of the manufacturing process. So you see that per definition, every single measurement that you are performing during your process and that gives you information about your process and helps you to understand your process and to ensure the quality is a PET measurement. So actually a simple compression force measurement in a tablet press is already a PET measurement. Might be an old-fashioned one, but it's a PET measurement. So PET doesn't have to be a spectroscopic measurement, but sometimes people think that PET is equal to, for example, near-infrared spectroscopy. But of course, today I will talk about spectroscopy. On the right side, you see a scheme of, for example, a wet granulation continuous line, and there you see what might be the possible PET positions. So if you could imagine, we have a line where we have, for example, feeders that are continuously feeding powder into the blender. Then you might be interested in a blend uniformity after the blender. When the powder falls into the granulator, then the powder is granulated, and then you might be able to measure particle size distribution. Later on, when you dry the powder, you might be interested in the moisture level of this powder. And then the powder falls into the tablet press where you can measure the hardness and the content uniformity. If you would use direct compression, you would save some process steps and of course some PET measurements, because if no process steps, no PET measurements needed. But before we start, I would like to give you some overview about why spectroscopy was actually the methods that now starts to be implemented for the PAT methods. And let's start the other way around. Let's define what are the most important points for a method which we want to apply in a process to measure fast and continuously. So the first thing is we should have a method where we do not need sample preparation. So you don't want to dilute the sample, just measure like it is. Then a second point would be that we don't want to have destructive methods. So because you want to measure quite often, and if you would destroy your sample, then you cannot sell it. So it should be non-destructive at the end. And then it should be cheap, of course. We don't want to pay a lot. And this method should give you the possibility to collect, to create some chemical information. So you want to know, for example, is it the right API? So the identification tests in my sample, or is the API concentration okay? But on the other hand, it would be great if the same method could deliver you physical information, like, for example, hardness of the tablets. And of course, it has to be fast because we want to measure in a process. And if we would now summarize all these requirements, the perfect answer to these requirements would be spectroscopy. And this is why PAT and spectroscopy are always so close together. But now let's go to some basics. So I will introduce you today some PAT measurement positions that we have. And during my talk, I will use two techniques. So actually, and this is our most common techniques in the spectroscopic world. We have always transmission technique and reflection. And transmission technique is you have the light source and you have a detector and the light goes through the sample. So we measure quite a big section of a sample, but you can already see it's the light has to go through the sample. So if we are restricted in a thickness of the sample, for example, for tablets, the restriction would be somewhere in 9 up to 10 millimeters thickness for NIR spectroscopy. But we can measure quite low API concentration with this method. The second method would be reflectance technique. Then the light beam and the detector are on the same side. So we are not restricted to the sample thickness anymore, but we measure only a small fraction of the sample. For most of the methods, we can only say it's only a surface method. But this method is less critical to geometrical shapes. So if you maybe have a convex tablets, or if you have a breaking line embossing, this method might be easier to apply. And this method is also better for moving samples. So you see, there's actually no the method. It's always depending on what you're searching for and what problem you want to solve. Then either the one or the other method might be better for you. So, and the last slide from a background and basics in PAT is also, when you talk to the people, they like to use this fancy words like offline measurement, inline, at-line, but not everybody using them completely in the right way. So let's just be sure that we are all on the same page. So offline means that we have in one room our process, and then we have a separate room, for example, laboratory, where the analysis is performed. So these two processes then are spatially separated. This is called offline. If your process and your analysis are in the same room, they don't have to be connected, but they can, then it's called at-line analysis. Online analysis is you have your process and then you have kind of a sampling loop where you withdraw the sample, pass with the sample the analyzer and go back to the process. Then it's called online. And inline is when you have an analyzer directly in your process, so you're not taking the samples out of the process. So before I would like to introduce you our PAT projects, I would like to show you our continuous manufacturing line, because this is the line I'm working with and where we perform most of our trials, so you can better understand the setup. And maybe before we go into this line, I would like to introduce or to present you why continuous manufacturing is now starting to get more and more interesting. And it's mainly because of the motivators and drivers I would like to present you now. So first of all, it's time to market. You can save time during the process development phase, because in a continuous line, you can vary the parameters. You can change the blending parameter and directly see what is the influence on the tableting. So you save time, you are more flexible. The second point would be batch size. You are not restricted to some equipment size anymore, like in a batch production. So where you have one big blender, and if you want to produce a smaller batch, you need a smaller blender. You just keep it like that. And if you want a bigger batch, you just run for longer. Then you maybe run for 20 or 30 minutes longer. Then the scale up process, you would develop the process on the same line, and you can also produce later on the same line. So this scale up process that you normally have in a batch equipment, when you start with a smaller tablet press and you have to scale up on a bigger tablet press, may disappear. So it can save you up to 6 months. The next point is, of course, product losses, because a continuous line can run for quite some long time. And the only points where you can lose the product is during the startup phase and stop phase. But you use the same powder during the startup up for all the unit ops. So you would save product, and when the line is in steady state, the line is running normally, usually. Additionally, you can control, and your quality of a product can increase, because you can control your product more in much more process in much more tighter limits than in a batch production. Because if something is wrong, you can still adjust the process and go back into the tighter limits, and therefore your product quality, due to PAT and maybe advanced predictive control, so-called APC, might be much higher. Then, of course, your CapEx and OpEx costs might be reduced, because you don't need to buy more equipment anymore. You don't need to buy several blenders to be flexible in batch size. You just buy one line and try to realize all your capabilities with this line. Because you don't have the intermediate product in between, you don't need place to store it. So you can save storage space. And additionally, you also have this so-called safety and ecological footprint for the operators. They are much less in a contact with powders. Therefore, it's safer for them. And I don't know if you've ever seen such continuous lines, but they are also quite tiny, not tiny, but small compared to huge batch production holes. So you would really save footprint. So they have a smaller footprint. And because it's a smaller equipment, you need less energy, you need less water to clean it. So also your ecological footprint is smaller, might be smaller with a continuous line. And now this is our continuous line from our testing facility in Schwarzenberg in Germany. And that's a high throughput line. What you see on a picture, we have also different lines, but the setup is for high throughput. And you have a two-level concept where we have the raw material charging. Then we have the feeders on the second level. We will also see it a bit better in a video, which I will show you quite soon. Then the powder falls into the blender. And then the powder, after it's blended, it goes into the tablet, and then it's tableted and goes to peripheral equipment. This continuous line is completely built on a FETTE controller. So the operator who is operating a FETTE tablet press knows how to operate the continuous line, because there is the same logic behind. And therefore, it's easy to operate. This line can run from 5 to 300 kgs per hour. You will see also today case studies for the whole range. And we have several PET techniques on this line to monitor the API concentration. And now I would say, let's start with the fun. Let's really look into the PET techniques. What I want to present you today is not a FETTE PET portfolio, no. So it's what we are doing on a research at the moment. So these are the projects that we are realizing together with the customers, that some of them are already realized on some projects. We're still working with the customers. And it's not that we have this solution for PET problems, but I just want to share with you our experience, because we were able to collect some experience, and maybe even have an interesting discussion. What is your point of view maybe on several implementation positions? Yes, and of course, because we're at FETTE, the implementation positions are mostly located in a tablet press. So it's not a continuous only technology. So of course, you can apply them in the same way in a tablet press. But I would suggest, let's just follow the powder stream. So we now see our blender in the background, and then the powder falls into the tablet press. So let's just follow the powder stream. And now the first powder arrives the tablet press, and it arrives the infi tube. And there you can see that we are now directly below the powder level. And here the powder is moving slow. So this position is quite good for slow measurement techniques. So you can of course apply near infrared spectroscopy, but for sometimes you want maybe to apply Raman spectroscopy. Raman spectroscopy might be more precise, and therefore you might be able to measure lower API concentration. So this position might be good for Raman technique. This is also a sensor you can see on a picture, but it's also might be suitable for laser-induced fluorescence. So we already have discussions with our customers and also tested several spectroscopic techniques in this position. And we are sitting here directly underneath the powder level. So it's easy here to monitor also the blending process, because it's really freshly prepared blend where you can see that. If you once get here a bed measurement, then you always have a question what to do with this bed measurement. Is it, of course, you can reject the powder, but then you need so-called real residence time distribution models, or RTD models. So you need to know, you need to have a model to know when this bed powder is here coming out as a tablet. But of course, you can have some kind of diverter. So there are also some companies who are measuring directly after the blender, before the tablet press. But we do not believe in this philosophy, because in a continuous line, you don't want to stop the tablet press. So the tablet press should run. So actually the whole continuous line should run. And if you would stop one of the units, then there might be already a bit out of steady state. So, and now if we would follow the powder, now we are in our feed frame in the philomatic. And it's our 3-chamber philomatic. And now you can see that we are in a second chamber in a filling can. And there you see an NIR sensor, which is measuring directly in contact with powder. And this is powder which is falling into the die afterwards. And in this position, we have a really great spectroscopical quality. We haven't experienced any sticking of the product to the sensor. You have the same, I would say, not issue, but a challenge that you have also with the position above. If you have a bed measurement, then you have to have RTD models, so residence time distribution models, to be able to know when this bed powder is in a tablet to reject it. And also to verify this measurement. So if you have once a bed measurement, which might be due to spectroscopic, because you have might be air in front, air bubble. Anyhow, you would never be able to collect exactly this powder and measure that. Now we are getting further. So the powder was compressed, and now the upper punches are going up, and the tablet is still in the die. And before the tablet gets ejected, there is a sensor which sits above the tablet. And you have to understand that tablet press is actually a perfect sampling device for PET, because it presents a tablet always exactly in the same way, in the same distance to the sensor. The tablets have the same hardness, so the samples have the same hardness. Therefore, in this position, we have a really good signal to noise ratio. And we can do 100% measurement control. And therefore we measure every single tablet. And if the tablet is bad, we can reject. So we can do single tablet rejection. We can reject this tablet, can take this particular tablet and go into the lab and do maybe verification HPLC analysis. And we can really align this reference analysis value with our spectra, because we know really which spectrum, single spectrum, belongs to each tablet. And the last position is now the tablets are out of the tablet press, and they're falling into the NIR Checkmaster. The NIR Checkmaster, this is now really a product of FETTE. So this one you can buy. So the NIR Checkmaster is a tablet tester where you can check all the physical parameters, like what you know from a tablet tester. It's diameter, it's hardness, it's length and hardness, breaking strength, and also the thickness of a tablet. But it also have an additional NIR device. I will show you that a bit more extensive on some slides later. And this NIR device is really precise, because here now we have time. We are not so time critical like we are in the positions I showed you before, because the longest measurement here is always a hardness measurement. So we can take time. Therefore, an FT NIR is installed in this position. This is a quite precise NIR device, which allow us to measure really low API concentrations. And I will show you a study later on. A company, not even ourselves, measured this and said that this device is can achieve the same accuracy like HPLC, because we have a hardness measurement, tablet weight measurement here, and also API concentration measurement due to NIR. We can measure content uniformity, and then we also consider this device as the easiest device to start with real-time release. If, for example, our customers are not really into PAT yet, because this device is already fully integrated into FETTE systems. So you will not get a scary spectroscopic screen in a production, of course in a development mode, but not in production. The operator just operates a FETTE tablet press and operates an NIR Checkmaster through the FETTE software. And it's easy and robust. So in the next step, I would like to show you a video of our continuous line. I just would like to show you the video because there you can see some of those PET tools in action, and I think that might help a bit and make it more interactive if I cannot show you it in person. So let's start with your video. Yeah, it's running. So it's our direct compression line. It's our testing facility. It's actually me several years ago. And this is a two-level technique. This is now, you see our HMI for this line. It's an older one, so I think it's 2 or 3 years ago. Now it looks a bit more fancy, but all the things that you have are needed here. You have an HMI to run the feeders, blender, tablet press, and also the PET tools. And if you like, you have an access to all the parameters of every single component, so you can adjust the parameters really in details. So, and now you see the feeder level. And you will see now that the powders will be filled in. And this is a level I was not able to show you on the picture before. And you see there's one feeder, and you see the second feeder. So the powder is now moving and dosing into the blender. And now you see that the blender is also already running. Now you see the PET tool. This is the first sensor. At that time point, we measured blend uniformity in the blender. But now, with our experience now, I would not recommend you this position, because you will see it in a minute. There is a lot of things are happening. So you see that the powder is blending. So you can imagine this is an NIR spectrum. You see, you can see the blend uniformity and follow the NIR spectrum. But you see that a lot of things is happening in front of the sensor, and therefore the spectra are really noisy, and the blend is not finished. So there is still 1 or 2 screws in the blender later on where the blend is still blended. So I would really recommend you to measure after the blender. Now we're already on a tablet press, and the tablets are already tableted. And now you see the NIR sensor, which sits between the tablets, and you see how fast the tablet press is running. And now I will just unmount the sensor, and you see that we also have some cleaning concept tubes. I will explain you that also later on. That's really important because we're in a dusty environment. If you would not have a cleaning concept, you will have a dirty sensor, which will show you nothing. That's our old screen. Now it's a bit more fancy in FETTE colors, where you see that you get a dot for every single measurement, and then you see that there are the edges. And if you're in a green zone, then operator knows that everything is okay. And if you're outside, then it's yellow and red at some point. And we also have an add-line tester. That's one of our NIR check masters. And you see that there are some tablets that are now going into the tablet tester, and they're tested at single positions. And now you see the NIR measurement in the position, how the sensor is moving and scanning the tablet for the measurement. So, and that is, it is actually, so as I said, I wanted to show you this video just to show you some of the NIR positions and maybe make it a bit more interactive, so you have a better feeling what I'm talking about today. And so this is just the video. I will just wait for 10 seconds and you will see a beautiful FETTE logo and produced tablets. No FETTE logo. Just let's go to the next slide. So, and now when we have discussions with our customers, so we talk to customers who are on different stages of PET. So some of them already know what to do. They don't need us. They just want to buy a unit and do everything on their own. And then we have a lot of customers who are new to PET and they are searching for a strong collaboration partner. And with these customers, we always tell them that you should not expect too much from PET directly from the beginning. So that's why also the talk is called The Road to Real-Time Release. We always recommend to start slow, because PET might be then a new device for you. And the first step would be actually process understanding and trust in your quality, because you have never measured your process so frequently. So you actually don't know what's going on in your process, and now surprise, you may have some variations that you have never expected. So take your time to learn and to trust into your PET and also to trust in your process. Then the second step would be, okay, now you're trusting your process, you're trusting your PET tools, start with process optimization. So start maybe to react on the process or to stop your process if you see, okay, the batch is bad, I have to maybe reblend, whatever. And as only the last step would be the real-time release. So when you see that you're trusting in your quality, you're trusting in your PET, your process is optimized, then you can start to reduce the lab testing. And of course, then you can also start to reduce also your inventory. This is an advantage of real-time release, because you can release a batch faster. So this PET can bring you a lot of advantages, but you just have to understand that it might be a long trip depending on what you expect from this tool and how difficult is your process. But if you would go on this, I would say, if you would take this road to real-time release or just use PET, it can help you. And PET is your eyes, so it helps you to see what's going on in your process. But now let's have a look on really single sensors or measurement positions I have presented you, and also in the case studies. So the first, I would just stay with the same procedure. We just always follow the powder and just look in the first sensor. The case studies that I will present to you will always have the same structure, most of them. So first, I would like to have maybe a more closer look on this particular sensor that we use for this case study. In this case, it's a Raman sensor. As I already said, for some applications, Raman might be more interesting technology because Raman is more specific. So it might be that sometimes if you have several APIs or if you have even several APIs that are similar in a chemical answer, then it may be useful for you to use Raman. And also if you are in a low concentration area, then Raman might be also the better choice. When I'm talking about low concentration, I think I will repeat it several times today, but normally you say that NIR works until 1% in a process. But I would say actually it works only up to 5%. So above 5%, I'm quite sure if you don't have quite a fancy API, it will work. But if it's not, if between 5 and 1%, I would always recommend to test, to do some feasibility studies, and below 1%, most probably in a process, no chance. But with Raman, you can go much, much lower. And for example, I will present you a study just in a second for low API concentration. And here you see some technical data. So you see that, let's just face on most important points. So you see that this is quite a slow method. We need 5 seconds per measurement. Of course, it's completely product dependent, and it's also supplier dependent. Who's your Raman supplier? So it might be fast, it might be much slower, but just as in a random value. And then the sensor needs 2 seconds until it can perform the next measurement. So for you just to know then how often you can measure. And in this case study, so I will always present you what was the setup. In this case, we have a target API concentration of 0.3% to do the calibration model. So quite often when we are performing feasibility studies with a customer, so we have blends of different concentrations, and we measure them on our continuous line together with our PET tools and with the customer. Then we create a calibration model, put the calibration model on a continuous line, and then we start to play by varying different parameters and see how, if we are capable with a PT to really see this difference and variations in the process. So first of all, I would like to present you a model. So because to be able to use PET, you always have to train the sensor. So you have to say to the sensor, the spectrum, for example, belongs to, I don't know, 10% of API. So you have to have calibration blends with different API concentrations, then collect the spectra, verify the measurement by maybe HPLC measurement, or if you do it quick and dirty, just assume that you have 10% in a blend and do like that. But so what you always see is the calibration curve. You would always see the predicted values. This is the values that are measured by the spectroscopic technique against the true values or the reference values. In this, this either the reference method measured value API concentration, or it is, for example, label claim of the blend. So then we will always look on some characteristics of the model. For example, its root mean square error of cross validation. It's actually an error of your model. It's, in this case, it was 0.05%. And the R square, it's, yeah, you know, it's how straight is your line, how good is a prediction. And you see that these values are quite great, but I will also say something to those values later on, so how to evaluate them. But for this product, we actually proved the feasibility. And after the annoying part, the fun part starts. So we use this model now on our continuous manufacturing line, and we run this product. And now we want to see what happens if we start to play around and start to make mistakes. And you see that the line was in steady state after 10 minutes. And then, wait a second, I have to see. My slides are in Spanish, and sometimes I'm a bit confused what's actually on the slides. So the point 1 is actually feeder inaccuracy. So that mean continuous manufacturing. You remember feeders on the second level. What we have done, we just hit one of the feeders. So don't hit the feeders. But of course, then we introduce a mistake. And this is a mistake. We had a disturbance in the process. And this is a mistake was perfectly picked up by the system. Then we were running for some minutes, and then we stopped the line. And I already said what continuous lines doesn't like if you stop and start them again. So don't do like that. But now we started the line again, and you see that during this process, we were a bit out of spec. So you see that we were a bit of steady state, and then we were in steady state again. And then we decided, because it's continuous line, just increase the API concentration. So we went from 0.3 to 0.38. And you see that after some time, so at 0.3, we changed the concentration, and you see then how fast the concentration changed. And then 0.4, we decided, boring stuff, let's go back to 0.3 API concentration. And you see that the concentration went back. So it shows that the model was able to follow to all our crazy changes during the process. So let's now go to the next position. And this is our PET in a feed frame. Once again, let's have maybe a bit closer look on the sensor. So you have seen already that the sensor is sitting in a second chamber, and you see that the sensor is really in a direct contact. And we also have a micrometer screw here, so we can insert the sensor a bit more or less into the feed frame. And this might be sometimes really useful because depending, or based on our experience, depending on a powder flowability and of course also which philomatic wheels are installed, it might be necessary to change the insertion depth of the sensor. And and also there is, beside that, there is also white reference implemented in the sensor. So because NIR technique has to be referenced at some point to be sure that the environmental conditions hasn't changed, and so on. So for example, you would reference your sensors with an external white reference once a day. But if you can reference it in a process, it will guarantee you that you will not have, you can correct for some drifts, for example, for temperature, for environmental conditions. So it's always good to have an internal reference or a referencing possibility for sensors on a continuous line. And yeah, and let's now look just on the technical reasons. So it's an so-called diode array detector. It's a fast technique. So if you want to use NIR in a process, most probably you will end up with this technique. And then the wavelength area is here, it's so-called extended NIR area. So NIR range starts, normally the sensor starts somewhere at 800 nanometers and go up to 2,200 nanometers. And so the first range, it's a normal NIR range, and the second range is an extended range. This sensor is working in an extended range. Honestly, my personal opinion, it doesn't matter which range you're using, because NIR technique and the APIs that we are using there don't have really this precise peaks, at least in a solid, so in oral solid dosage forms, not such precise peaks that you really need a special range for that, or at least based on our experience until that point. But of course, if you're coming from a different area, not from OSDs, then it's really interesting for you. But in this area, so extended range for this sensor is where a lot of specific peaks for special API can be found. So, and if you will go to a normal range, then you maybe will have less that peaks, but you would have a good spectral to noise ratio. And as I said, from my personal point of view, you can always use both. It just depends on what is your target. So now you know already how, the game. So the calibration model for the feasibility study. And you see it's our, this time the model is based on 5 API concentrations. Root mean square error of validation is in this case is 0.34%. Is quite good, R square, and we have 2 latent variables. I would like to tell you something about these values. So everybody likes to discuss about these values, and also agencies want to see these values. But my personal recommendation always, don't try to get these values as low as possible, because if you try to get them as low as possible, at some point it can happen that you're losing robustness. because NIR sees everything. So if you, NIR is able to react to changes of your particle size, for example, of your raw material ingredients. NIR is able to react if you change the humidity of your raw materials, if the temperature changes, but you don't want these parameters to influence your prediction, your measurement of the API concentration. So they should not be included in your measurement. And therefore, sometimes it's better to have more robust and maybe not so precise model, because later on this model would. So what I'm talking about is more, when you do a model, really pay attention to what the model is reacting, and maybe do not try to include, because all values are actually correlating with each other. Maybe try to include less latent variables. So this number should be actually as low as possible. Try to include as low amount of latent variables as possible to have a good model. And now you have the model, once again, predicted API concentration against reference API concentration. If you see these models, it's always important to see that you have a straight line. That's good for linear correlation, and that you do not, your dots are not varying too much around the target concentration. So in this case, a bit varying, just because we used in this case not a reference method, but we used the nominal blend API concentration that we thought is there because we put it into it. It's not that precise. So, and now we put it on a line once again. So in this case, we had approximately 67% of API concentration. I'm not allowed to tell you the exact one. And then the line was running, and we induced some disturbances, like you already know, and have seen if it was picked up by the line. And our most fun part that we really like is to change the API concentration. So we went to 65.5% of API on the at the time point of the red arrow. And then you see that the concentration dropped. And then we actually thought, okay, it's already there. So we went up again, but it was not there. So the concentration dropped for some time again. And then it went back to a steady state, and then we stopped the line. So, and now let's go to our third measurement position on a tablet turret. You have seen this sensor once again in a video. And now I would like to describe you the sensor a bit more. So what we have here, because we have a lot of tubes and a lot of cables there, we have two black tubes. These are the light fibers. So this is where the light is coming from. Then there is a gray tube that you do not see at the moment. This is the light fiber going back to the detector. So it's your measurement results going back to the detector. And then you see this blue tube. This is the cleaning concept. So you have ear nozzles, which are cleaning the window of the sensor, because as I said, it's in a dusty environment. It's really important that your window stays clean. In an actual version, which we will release soon, we will have the cleaning concept on the other side. This is also the ordinary technique. So it's because we need it has to be fast. This sensor can be bought in a full range, so it can cover standard and extended range at the same time, but it can be also bought for one of the two ranges. Personally, I would always recommend you for this sensor to take a standard NIR range, so something from 900 up to 1,700 or something, because there you have a higher light intensity. This technique has a better signal-to-noise ratio. And you can imagine, so such a tablet press can be really fast. And this sensor has no speed limitations, but it has, of course, might have spectroscopic speed limitations, because at some point you have really maybe just 1, 2, or 3 milliseconds to measure. So 3 milliseconds, actually the whole range is comfortable. We can measure with the whole range, but if you really running full speed on a fully equipped huge tablet press, it might be more reasonable for you to go to a normal NIR range, because here every millisecond counts. It has a high spectral resolution. It's validated against USP, and there's the last point. And we measure every single tablet, as I told you. Now let's see some case studies. So the case studies are were performed by a university, and this is an IR sensor which was located on our small tablet press on a FETTE 102i. It was on a continuous line, and the API concentration was 25%. They used the full speed of the tablet, so the whole range of the compression speed, to see if the sensor is suitable to measure. And they changed the compression force and the tableting speed. So this is how the raw spectrum, it's the first time I think I'm showing you the spectra today. This is an NIR spectrum. It's an absorbance spectrum in the wavelength area of 1,100 up to 2,100 nanometers. And you see here the raw spectrum. And if you would now apply some multivariate data analysis for an analysis of that, these are the tools that we in most of the cases need to analyze a near-infrared spectroscopy spectra. In this case, it's so-called partial least square, PLS method. So what it's doing, it now reduces the spectrum to only one single dot in a new dimensional space. So in this case, it's two-dimensional space, and each spectrum is now represented by one dot. So, and you can imagine one spectrum always correlates to a certain concentration. So now one dot correlates to this certain concentration, and you see that this spectrum belongs, for example, to 22%. And you also see that the spectra can be actually are clustered nicely for their API concentrations. So you can nicely separate between the API concentrations, and that means you can also build a model because you can differentiate between them. And this is a model. So we have predicted API concentration against a reference API concentration with a root mean square error of prediction 0.75. Maybe also a short comment. I'm talking a lot about the root mean square errors, and there's always a different letter behind, but most of it's just the reason how these values were verified. So it's which validation method was used, was a test set used. I don't want to be there too much in detail, but more or less today you can compare these values. And this is the model. And what I would like to show you more is now also an additional study. It was performed with lactose as a model API. So it was actually, this study was performed during a customer event. So the customer was playing on the continuous line and destroying the whole model because they were just adjusting the parameters, and we were just looking what happens. So the line was running on a 10 kg. The API, which in this case lactose concentration, was at 50%. And we have varied several parameters. So in the beginning, this is the first arrows. As a customer was just changing the tableting speed, the philometric speed, and then one or two tablets were just different than the other tablets. And this is what you can pick up and clearly see with the sensor. Then after some time, once again, our favorite game, we changed the API concentration from 50% to 58%. And you see that after 7 minutes, the API concentration increased. And then, it's my second favorite game, hit the feeder. We actually induced error to the feeder. And you see that the feeder overreacted for some time. So we had some tablets with too high lactose concentration. So, and now we are almost done. So my last API position that I showed you today was the NIR Checkmaster. Now let's have a more detailed look on this API, on this device. As I already said, we have now here a really precise NIR device, which have a really high spectral resolution. And it's a transmission device. So we measure through the tablet. The light force sources underneath the tablet, the detector is above the tablet. The measurement is quite slow. We have 16 seconds, but we do not care because the hardness measurement is anyhow slower. The setup of the study was that we have produced the tablets on our tablet press of 6 different concentrations. This tablets then were later on measured with NIR Checkmaster, and the same tablets were also measured with the HPLC. And and I would like to show you now on this page how the NIR measurement is performed. So after the physical measurements are performed, the tablet is grabbed by the holder and it goes into the so-called snap holder. So it moves in and then the tablet is snapped by the holder and is fixed. And I told you, you may remember in the beginning, that transmission is really critical to geometrical shapes, to embossing. So the tablet has always to be positioned exactly in the same way. And by this patented holder, it is possible. So the exact positioning, and also we can reduce the straight light. So you can imagine if you have a tablet in front of the light, then the light can just easily go on the sides above the tablet, but this light has no information, it will just blind your detector. And therefore this holder blocks this light, the so-called stray light, and the light cannot go around the tablet, the light can only go through the tablet. And that allows us a high precision measurement with this device. And now the study, this is a study we performed with a big pharmaceutical company. It was published a year ago. And this, I'm not allowed to tell you the exact concentration. So we are now talking about concentration levels. So you have here the API concentration, and then you have a blue bar, which is NIR Checkmaster, and the orange bar, which is HPLC measurement. So the same tablets, but now on 4 different blends. So it's our test set, our verification set. And you see that for this test set, we were able to detect exactly the same concentration, what is already good, than HPLC. But you can also see that we have smaller standard deviation than the HPLC. So the results of the company was that NIR Checkmaster is able to predict the concentration values with a comparable standard deviation than HPLC due to the holder, because it avoids the scatter light. And what I maybe forgot to tell you is that the NIR Checkmaster is completely integrated into FETTE software. So the operator is not in a contact with all this frightened spectroscopic stuff. He only sees the dots on the screen. And because everything is integrated into our batch report, where you can see that it's easy to for the documentation. For this device, I would like to show you a second study. It's our for the API concentration of 0.33%. And in this case, we once again have an API concentration. I just skipped the model. Trust me, the model was good due to time, because of the time. And we have different tablets. So we followed the process once again and have seen that the NIR is possible and the model is possible to pick up the variations in the concentration. So this is once again what I said in the beginning. Please don't forget API constant NIR in a process. So really measuring in a process, in a powder stream on a tablet in a process is more or less up to 5%. But if you have time and if you have a high precision NIR device, then you can get lower, then you can get even lower than 1%. And the last study I would like to introduce you is that we use 3 of our sensors. That was the most fun. If we have them, we can also use them. And in this case, it was already quite challenging concentration because we had 3% of the API. And you remember NIR, not below than 5% in a process. So for Raman, easy game. Raman should be able to do that. For NIR, a bit challenging. We had all the 3 PAT tools on the line, and we used 5 blends for the concentration, for the calibration model for each sensor. I will skip the models for each sensor, but trust me. And now let's see the results. So once again, it was actually performed on a continuous line. We like to challenge the line. So this time we just wanted to do what the line doesn't like, start and stop, start and stop. And we have performed it several times, so several breaks in between, even a bit more. And then we started the line and just wanted to see how the line is run. So the line was out of steady state by this doing that. And you see that this difference is clearly seen in a Raman. So in the in the infit tube, you can see that we have an increase of the concentration. Then you see in a feed philomatic that it's followed, and you see that now it's a bit more flattened because the philomatic blended the powder a bit, but you still see this clear disturbance. And then once again, you can see that in the visionary, so in the last NIR sensor on the turret, that it's now even more flattened, so the feed frame blended a bit more. But you still can see that we still have some single bad measurements. So it's really bad tablets that were rejected in this case. So not everything from this disturbance was even out, and we were able to pick up this single bad measurements. And I think I'm actually now done with my presentation. So thank you very much for your attention. And now I look forward to your questions.
Thank you very much, Anna, for that great presentation. Okay, thank you very much, Anna, for this great presentation. It was very informative. And now we do have some questions for you. The first question we have is, how is the cleaning frequency established in these continuous processes?
Cleaning frequency, do you mean cleaning frequency of the PET, or do you mean cleaning frequency of the PET of the continuous line?
Well, that was one of the questions from one of the people that we have watching the webinar. So it would be, I don't know if it's going to be in general or.
I will try to answer both. So if you mean if you mean the PET tools, so then it depends on a position. So for example, the positions, the tools which are placed next to the powder, where the powder is moving, you don't need to clean them. They're cleaned really by the self-cleaning effect of the powder, at least based on our experience. And we have already compressed some sticky material. The sensor which is placed on a turret, there we have a cleaning concept, and there's a compressed air. It's there all the time, because if you would turn it off, then it will be permanent dusty. And in an NIR Check Master, we have an air nozzle which cleans the sensor in a frequency that you can adjust in a FETTE software. To continuous lines, if you mean the cleaning frequency of the continuous lines, it's completely your product dependent. So I cannot tell you that in general. We for example, I can just give you some examples of the customers. So some of the customers prefer to stop the line after 15 hours and maybe do some vacuum cleaning, mainly as a tablet press, and then continue to run for additional 15 hours. Some of the customers are at the moment aiming even to run for longer. So it's more about your process, how good is your process adjusted, because the main and which components you have. If it's sticky components, then maybe you may have the problems that you have a powder build up in a tube or something, but we have solutions for that. But if it's a dusty product, or maybe your tablet press not adjusted right, then the tablet press is too dusty, then you have to do the cleaning. So it's completely dependent on your process and your tableting. But yeah, maybe my example with a customer will help you.
Okay, well, thank you for that. Now we have another question here, and it says, will these devices allow the validation of the analytic technique?
Sorry, I haven't understood it acoustically. Sorry for that. Can you repeat the question,
No, it's
please?
okay. It says, will these devices allow the validation of the analytic technique?
Yes, of course. So these devices are allowed. You can validate them with analytical methods, and also the regulatories are now getting more and more pushed by the market, pharmaceutical companies. So they start to be more confident with these techniques, and are so there are also already some released methods that are approved by the regulatories. And as I said, you can validate them. You have even monography in the USP Pharmacopoe, where it's really written what you have to do with the sensors so that they're validated, and then you just validate them by the methods. There's also a guideline how you validate such spectroscopic model before you supply it to the regulatories.
Okay, perfect, great. Okay, so the next question we have is, how can the regulation be met when it comes to this type of analysis?
for example, if you mean regulation, so do you mean regulation of the process or regulatory thing? But I assume regulation of the process. Regulatory, so authorities. Okay, so if you have this kind of process analysis or this process control tools on your line, then as I said, there is a guideline. So I know that there is a European guideline, and there should be also the comparable guideline in the US, so from FDA. And this guideline actually tells you step by step, not really step by step, it's a guideline, but it helps you already what you have to do to be able to validate that. And there is a, really, it tells you, for example, that you have to prove that the measurement was applied to the, or the model was applied to the right spectrum. So this analytical device, for example, they perform some spectroscopic check to be sure that there is no air bubble in front. So you have to say, yes, I have done the spectroscopic check. Then you also have a question in the guideline. It tells you, okay, you have to prove that you know to what is your model reacting. So you have to go to the regulatories and say, look, based on my model characteristics, I know that if the API concentration is changing, also my prediction, so my model reacts and tells me, yes, it's changing. But for example, if the hardness of the tablet changes, it's not reacting. So there's a lot of points, and it's not new to regulatories, not to all. So, but at least in the United States and also in Europe now, it starts to get more and more. But as I said, so please don't already, so take it as a road, as a process. So don't start already with regulatories in the beginning. So maybe start at the beginning to understand the technique. But on the other hand, start the dialogue with the regulatories as early as possible, because they actually also want you to implement this tool. They understand the added value of this tool. They will also help and guide you through this, or at least it's our experience with our customers at that time point.
Okay, perfect. We have the last question here. Can you recommend a book that talks about real-time release of production processes?
Oh, interesting question. I don't have a book in mind at the moment. I don't even know if there is a book which is up to date, because a lot of changing in this world. What I would really recommend you is more publications. Recent publications. I'm just thinking who might be. There's a lot of universities who are interested in that and pay attention to that. There's a lot of pharmaceutical companies. So I would definitely recommend you to search for Johnson & Johnson. Janssen presentations or papers, they have a lot, and they have also presentations which explain how their model look like, that they get a real-time release approved later on. And I can also recommend you to look for Pfizer presentations, and also Novartis. There's also a nice presentation together with FETTE, and also paper. So I would really recommend you maybe to look into the papers, and then just follow the biggest pharmaceutical companies who already quite innovated in this area, and you will that might help you already a lot. And if you have some questions, you can also, of course, contact us.
Okay, perfect. Thank you very much. We also have another question here. They're asking if the PAT can be purchased independently to be used for in another type of machine.
Yes, of course. So as I said, what I have presented you today, it's not our portfolio. It's just PAT tools that we have just bought from some third parties, some of them at least, and just installed into our tablet press. But I have showed you two tools that are more or less FETTE exclusive. So this is a PAT tool on a turret. This one is really can be only used with FETTE tablet press, it's patented. And the NIR Checkmaster as a Checkmaster can only be used with a FETTE tablet press. But of course, there's also some competitors who are also doing similar devices. So it's completely independent. Yeah.
Okay, thank you. We also have another question here. Are these at-line results enough for approving a batch?
Yes, so at least there are already some customers out there who are using similar devices to approve the batch, but don't forget, so when you approve the batch, you have several tests, so it will not help you with all the problems, but it may help you with identification so that you know which API is on the line. It may help you with assay, so API concentration, with content uniformity, so CU, and there was a forced, it can, if you're really, really lucky, it can help you with a dissolution, but it's really advanced stuff. But there are companies out there who were able to get this at-line technique for actually for presentation, for the real-time release, even for the dissolution. What is not reported yet in a pharmaceutical world is that you can also use this technique for impurities. That's a challenging, then you maybe still need your lab analysis.
Okay, perfect. We also, there's another question for this same person. And they're asking if the quality control will be totally dismissed, like by using the PAT.
At some point, I would say, yes, it can be not really dismissed, but you will just do your quality control with an NIR checkmaster. I would still recommend to keep your lab analysis also in the beginning, because for example, your raw materials can change. So it's still recommended to collect some spectra and to record new spectra and do reference analysis and align the samples. So do verification of the model maybe once and a half a year. So you should keep your HPLCs in the lab. Maybe not that much anymore, but keep one.
Okay, well, thank you very much, Anna. That was the last question that we had for you. It was actually our pleasure to have you here. We are so honored to have you as part of this Farmaweek 2020. We really appreciate your participating here.
Thank you very much. Thank you for the invitation. I really appreciate it. I hope you had fun, and yeah, thank you very much.
Thank you.
Bye.
Bye. Thank you. Bueno, muchísimas gracias a todos ustedes que siguen ahí conectados con estas conferencias. Ahora vamos a reiterar que este evento llega a ustedes gracias a Farmacia Carol Group, por ser parte de este encuentro, y por ahora haremos una pausa y retornaremos a las 2 de la tarde con nuestra siguiente conferencia del día de hoy.
Gracias por entrar a Farmaweek 2020. Nuestra próxima conferencia es